Okay, so in my lab 2.5 folder here, I'm going to right click and create a new file. Actually, does this have a net new file? Yeah. Let's see what this does. .NET new file. Oh, okay. And then it takes me into this to say, hey, it's class. I do want a class, and I want it to be this union find. So this is class union find. And I do want this to be generic in T. And I don't want this console app1 namespace. I want it to be in this namespace. So I'm going to copy that and put it there. And I'm going to call it unionfind.cs. Ugh. Does that work for y'all? Is this bothering anybody else? Okay, just me. Oh, really? This feels like the most unholy thing that I've done in code in quite some time. Okay, you ready? This is the essence of this data structure. We're going to have two dictionaries. You remember a dictionary is the C# equivalent of a hash table. And to be most resilient, like the most reusable, I'm making this data structure in T. So that means you can do union find groupings of any object T. T probably has to be hashable, but we'll see. Okay, so I want two private dictionaries. I want a private dictionary that goes from T to T. That's that bottom one that I'm going to call parent. You could call it parents. I'm going to go with parent. So this stores basically for each node who's its direct parent. And we're indexing, we can index the dictionary, right, by the node that we're looking up. The other thing that we need, oh, I'm not here. Can anybody read it and see who it is? I can't read it. If it says David Shannon, I'll answer it.
It says Cliff Thompson.
I need to pass. Okay. Do you want to answer it? That would be so freaky. Okay. I'm sure I've dropped a ball and Cliff is reminding me of it. The other dictionary is the top one, which is indexed. The key for that dictionary is what data type. So the key is how I'm indexing every element in that array. What did I put as my, thank you for saying something. No. The what? This is the rank dictionary. So I'm saying the key is what's like what I wrote underneath, which I only did 3 of them. The value in this dictionary is what is actually in the boxes. So does that make sense that it's the key is T and the value is an int? And at least my example called this the rank, which is sort of like the height. Okay. We're going to create a constructor, public union find. And I found this example that I do think is nice. We're going to take in an I enumerable. Is that how you spell enumerable? I think that should be a U. An enumerable is a really, really general interface that just means that you can for each iterate over the elements. So this thing that I'm passing in here really, it's got to be an I enumerable of T. This could be a list. It could be a list. It could be an array. It could be any data structure that you can enumerate over. You with me? So it's even less restrictive than a list, which is kind of nice. Okay, so this is the setup. The first thing I have to do, and to me, this is what you always going to need to do, is for these dictionaries, either here in the constructor or out here as a field initialization, you've got to give those memory. Right? At the moment, they're null. So parent needs to be a new dictionary of T, comma T, parentheses, such that it has a memory location. Yeah? So now we actually have parent. Same thing for rank. We need it to be an actual dictionary that has memory. Yeah? So now we got these two empty dictionaries. Now, they're going to be indexed the exact same way, which is every element in our potential world has an entry. So our potential world, you can see I put it on the bottom there, is KC, AN, EV, CC, like everybody's name. All the possible elements in the global possible set. So I want to say for each T element in the elements. So what I'm passing in here, in this first constructor, is a list of all the possible items that exist. Okay. I guess you could add some more after the fact, but it would be less efficient. But maybe that's okay if you don't know everything up front. In our case, we do know everything up front. Listen, we know all the possible entities in our system. Yeah. And what I want to do is I want to say the parent for this element is what? Remember, you can see up here, a parent is a dictionary that goes from T to T. So what's the initial? I'm initializing here. Initializing both dictionaries. What's the default starting point for the parents? I think I did it on the board. Itself, which that's just the element that you're on. In a similar way, I want to make the rank for each element to have an initial starting point. And despite what VS Code is telling me to do, I think I want to mark it as a 1. I bet it probably doesn't matter. You could probably do it 0 or 1 because the choices you're going to make are just based on which one's lesser or greater. So to me, this is representing the idea that if you have a rank of 1, you are your own parent. You're the top of the tree. Once you have a parent who has a parent, then your rank is going to need to be more than 1, like 2. Okay, so this is our initialization in our union find. Let's look at our really, we just have 2 to 3 methods that matter here. Okay, I'm going to get rid of my terminal. What's this? That is the constructor. Can I hide the constructor, or are y'all still looking at that? Actually, why do I get... I think somehow I turned off all autocomplete, and now it's just like dead. Okay. No, there it is. Okay, I want to have a public find. And I want to be able to take in an item of type T and determine, notice this, find the topmost parent. So I don't know the right word for this. Annika's word was the representative. The representative, was that it? Do you see what I mean by the topmost parent? I want to go all the way to the top because that's the guy that represents this whole group. In some sense, then you're using that parent, the name, the ID of the parent to mean this is the name of the group that I'm in. So all we have to do here is just go up until you find an element whose parent is itself. So here's an implementation of that. I can say if the parent array at item is not dot equal to the item itself, then the parent of this item is equal to, the parent of this item is equal to find the parent of the item. You see that right there? What do you call that? Recursion. Isn't it beautiful? So we're going to push this up, and they would say that what we're doing here by saving this back in here is path compression, compressing the path. Okay, so when we get here, how can we get here outside this if statement where we call the method from itself? We can only get here if this was not true, meaning the parent was itself. So in this case, we can return the parent of the item. Now you may have noticed there is an edge case here. And the edge case would be, what if somebody passes in some item that doesn't exist at all? Then we will never get out of this. So we probably need a statement here that says if the parent dictionary does not contain the key for this item, then we should probably throw a new exception. Maybe this is an argument exception that says item, I want this to be the $ thing, right? Item was not in the union find structure. You okay with that? Because if you try to look up an item that doesn't exist here, if you try to index to an illegal value, it's going to crash. So don't let the recursion or anything fool you here. This is simple. I believe we're just saying find your parent, find your parent, find your parent until your parent is yourself. This is a recursive way of doing it. You could rewrite it iteratively if you preferred. Just a while loop, right? Okay. The other important function that we have, this has a data type. This is going to return a T, right? This is, when you find this, it's going to return your topmost parent, so it needs to return a T. Sorry about that. There should be a T there. You see this T I added? All right. The other big operation is union, and you remember what does union do? It combines two items and whatever sets that they're in. So I'm going to have a T item 1 and a T item 2. Let's do this a bad way and then let's fix it, or at least kind of potentially inefficient. Okay, kind of what I did on the board was the bad way on the first way, which is what if we just said, put item 2 underneath item 1. Just always do that. You could do that and just ignore the whole rank thing. If you did that, you might end up getting a really long tree. But let's see what that would look like. So the first thing we need to do is we're going to find the root for item 1. That is to say, right, the root of the tree, the topmost parent for item 1. You okay with that? So, I mean, imagine one of our people here. Let's take Evan, and we'll go all the way up to Evan's parent's parent until it's itself. Maybe that's KC. That's the root for that item. I also want a root 2, which is finding item 2's rootmost parent. I already have my find, right? And it's going to run up the tree until it finds the rootmost parent. So now we want to combine these two, and I'm saying naively, we could just say the parent of root 1 is root 2. Sorry, that's sort of the opposite of what I said, but either way, the parent of root 2 is root 1. To just attach no. I want to make the parent of root 1 item 2. Yes. But this is still not the way I really want to do it. So this would work, but then I would always be kind of like adding this item 2 underneath. At least I would be, I mean, I guess the worst that I could do is to say something like that, right? And add the item under the other item. That's kind of what I did on the board. If I do it in root 1, this is actually already a lot better because now I'm attaching this new item directly underneath the other item's root. Yeah. Here's maybe the big smart deal way of doing this is using the ranks to make sure that we kind of balance this out. For one, I need to make sure to begin with that root 1 and root 2 are not the same. What does it mean if root 1 and root 2 are the same? They're already in the same group. And we're going to say if they're already in the same group, we're not going to do more work. So if root 1 dot equals root 2, and there's a not here. So if it is not equal, then I'm going to do some work. I guess you could invert this and say if they're equal, then return. I actually kind of like that better. Don't you? I don't know, almost be inclined too to not use curlies. You okay with that? Some people would even write this without a new line Is this crazy? I don't know. I kind of like the new line and the indent. Do you remember this rule? If you, in a C language, C-based language, if you have one line underneath an if statement, then it is in the if block. But as soon as you write another line, like this, even though I indented it, this isn't what your code's going to do. Your code's going to do this without brackets. But in this case, I'm confident there's nothing else that needs to happen here. You return if they're equal. So because they're basically right. This means they're already in the same group. Okay, so if we get here, they're not in the same group. So I'm going to say, I'm going to look up the ranks. So what's the rank of root 1? And if the rank of root 1 is greater than the rank of root 2, then I'm going to attach the smaller tree under the larger tree. Let's see if this makes sense. I'm going to write it and then let's think about it. So I'm going to say that the parent of root 2 is equal to root 1. And otherwise, I'm going to say the parent of root 1 is root 2. Hang on. There's another. If the rank of if the rank of root 1 is less than the rank of root 2, then I'm going to do it this way. What's this last else block doing? They are the same. So when we have a tie, what do we do? And let me see if this makes sense. I'm going to say that the parent of root 2 is root 1. And I'm going to say that the rank of root 1 is incremented. So I'm incrementing the rank when I do that. Let's see, I got 7 minutes. Okay. You feeling that? Let me show one more method and then we'll wrap up. I would like to do this. Are these two things in the same group? And apparently, probably the graph theory people would call this connected. So I'd like to know, are item 1 and item 2 connected? Are they in the same group? That's what I wrote as same group up there. What does it mean for two items to be in the same group? How can we easily determine that? Yes. So I can do this in one line because it is the case is finding item 1's rootmost parent, topmost parent. Is that the same node as finding item 2's topmost parent? If they're the same, then yes, they're connected. And if they're different nodes, then they're not connected. So I can say find item 1 and say, does that dot equal finding item 2? looks a little weird. I think you can't use equals equals because equals equals might not be defined between two t's, but dot equals is defined. I think that this is our code, and ooh, you know what y'all should do? Y'all should write unit tests. Wouldn't that be epic? To write unit tests, that should be the assignment because I already did the whole assignment. We did the whole assignment together. Maybe this should just be homework too, with the heaps. It's coming into focus now. That's what I should have done. Okay. Let's just try this and see what happens. If we were to create a new var uf is equal to a new union find. Anyway, we've got to have a bunch of stuff to put in. Right, we said you can only create a union find when you have the elements. So let me say I have some elements. Elements is equal to a new list of strings, and those strings are, wait, can I do it like, I think I can, this, A, B, C, you could put our initials if you prefer, B, D, F. That's a list of strings, and now I'm going to pass these elements into the constructor of the union find so that it's then going to create this dictionary that stores all those. I should probably build this to make sure it works. I bet I've got compilation errors. Yes? You got compilation errors? Oh, in order to use a union find, I have to say this is in string. And oh, this should be dot equals. What's the other error? Did I do it twice? Yeah. Sorry. Equals. Okay. Put an S on equal. So then to do this, we could just say UF dot union, and we could add A and C. Yeah? So now A and C are in the same group? Sure, let's do B and D. And then here, you want to ask, are A and D, are they connected? And to answer that, I would say UF dot connected A and D. That should be false, right? Why can't it see the one project that's there? Is that? Oh, because I'm not in that. Sorry. If you go into this folder and then do .NET build and then .NET run, this should run. Oh. False. Yeah. False. And then if I union B and C and do the same statement again, it should be true, right? Because now that B and C are connected, that also means A and D are in the same group. So let me build, run. It's true. Okay, so I'm going to send you a lab that has both heaps and union find data structure. You're going to get to write most of the heap stuff. Let me know if you have questions about that. We might touch on that on Thursday. And I want to introduce one last tree structure called a trie on Thursday. And then I'd like us to take a test like next Tuesday over all of our tree stuff. You down? So tree test a week from today. We'll get to learn one more data structure Thursday and make sure we're feeling this. When's the BST lab due? No one? Saturday? Okay, we can maybe address some questions on that as well. I think the data structure, the trie that I'm going to talk about on Thursday, will be on the test loosely, but we're not going to code it up. Thanks for hanging with me. I'll see you guys.